Long before humanity had the technology to watch the skies with precision, something extraordinary may have passed through our cosmic neighborhood. A wandering star could have entered the outer reaches of our solar system, disturbing distant objects and leaving behind clues that scientists would only recognize much later. Humanity never saw it arrive and never watched it leave. So how do astronomers know it was here? In this video, we follow the evidence of a forgotten stellar encounter. If you enjoy mysteries hidden in the universe, like the video, subscribe to the channel and join us as we uncover the star that passed through our solar system unseen. The sun moves through a broad and changing neighborhood of the Milky Way. From Earth, the stars appear fixed in familiar patterns, but this stillness belongs only to the short scale of a human life. Every star carries its own motion. Some drift almost alongside the sun, while others cross its path at different angles and speeds. The constellations slowly stretch and dissolve as these motions accumulate. Over tens of thousands of years, nearby stars change their positions noticeably. Over millions of years, the sky becomes a different arrangement altogether. The sun lies within the Milky Way's thin stellar disk, about 26,000 light-years from the galactic center. This disk contains stars' gas dust and the remains of older generations of stars. It is a vast rotating population held together by gravity. The sun travels around the center of the galaxy at roughly 230 kilometers per second. Even at that speed, a single orbit takes more than 200 million years. During one galactic circuit, the solar system passes through regions that differ in stellar density, gas content, and gravitational environment. The sun occupies a minor spiral feature, often called the Orion Spur, located between larger spiral arms. Spiral arms are not rigid bands carrying the same stars forever. They are regions where stars and interstellar material become more concentrated for a time. The sun moves within this wider pattern, while also rising slightly above and falling slightly below the central plane of the disk. Its path is therefore not a perfect circle. It is shaped by the combined gravity of the galaxy's stars' gas, dark matter, and central mass. Near the sun, space remains extraordinarily empty by ordinary standards. The nearest star system is more than 4 light-years away, and most neighboring stars are separated by several light-years. Yet this emptiness is not complete isolation. A light-year is the distance light travels in 1 year, almost 10 trillion kilometers. On that scale, even a separation of several light-years belongs to the same local stellar environment. Gravity acts across those distances, though its influence becomes weak, and the motions of nearby stars can be measured with increasing precision. The local neighborhood contains many kinds of stars. Red dwarfs are especially common. These small stars produce little visible light, so many remain difficult to notice even when they are relatively close. Brown dwarfs are fainter still. They form in a manner similar to stars but do not possess enough mass to sustain ordinary hydrogen fusion in their cores. Their weak infrared glow makes them easier to detect with instruments designed to observe heat rather than visible light. Many stars also belong to pairs or larger systems. 2 stars in a binary system orbit a shared center of mass as the pair travels through the galaxy. A faint binary can pass through the local neighborhood without appearing prominent in the night sky. Its physical importance does not depend on how bright it looks from Earth. Mass, distance, and relative speed determine the strength and duration of its gravitational influence. The sun's neighbors do not travel as a single, orderly group. They share the general rotation of the galactic disk, but each has an additional motion inherited from its birth and altered by later gravitational encounters. Molecular clouds, star clusters' spiral structure, and the galaxy's overall gravitational field slowly redirect their paths. A star that is distant at one time can become comparatively close at another. The Sun is also moving, so a close approach results from two paths crossing through the same region of space during the same interval. Astronomers describe a star's movement using several measurements. Parallax is the small apparent shift caused by observing a nearby star from different positions along Earth's orbit. It reveals distance. Proper motion is the gradual movement of the star across the sky. Radial velocity measures motion toward or away from the Sun through changes in the star's spectrum. Together, these measurements provide a three-dimensional position and velocity. They allow astronomers to calculate where a star has been and where it is likely to travel. These reconstructions are not perfect. Every measurement carries uncertainty, and the galaxy contains gravitational influences that cannot be represented in complete detail. The farther a calculation extends into the past or future, the wider its possible range becomes. For relatively recent passages by nearby stars, however, good measurements can produce a well-constrained path. Modern astrometry, the precise measurement of positions and motions in the sky, turns the local neighborhood into a moving map rather than a fixed picture. ESA's Gaia mission greatly expands this map by measuring the positions, distances, and motions of enormous numbers of stars. Ground-based observatories contribute radial velocities and detailed spectra. Infrared surveys reveal objects too cool or faint for ordinary visible light searches. No single observation provides every part of a star's motion. Close stellar passages are natural events in such a moving population. Most occur at distances too great to alter planets or cause any visible disturbance. A star does not need to approach the region of the planets to count as a close neighbor in astronomical terms. The scale of a planetary system extends far beyond the familiar worlds, and the Sun's gravitational influence reaches into remote space. Even so, stars usually pass one another with enormous gaps between them. Direct stellar collisions in the solar neighborhood are exceedingly unlikely. Encounters within several light years occur more often than encounters within a fraction of a light year. Low-mass stars can be especially difficult to identify before accurate surveys reveal their motion. Some move slowly across the sky because their travel is directed mostly toward or away from the Sun. Without a radial velocity measurement, such a star may appear deceptively quiet. Its true speed through space can remain hidden behind a small sideways drift. The galactic neighborhood therefore resembles a deep, slow current. The Sun and nearby stars move along separate courses, each responding to the broad gravity of the Milky Way. Their paths sometimes draw nearer and then separate again. No boundary marks the moment when one star becomes a temporary neighbor. Distance changes continuously, often over many thousands of years. Human history occupies only a narrow interval within this motion, while the stars continue along trajectories that began long before recorded observation. At the farthest reach of the solar system, there is no wall surface or visible line separating the Sun's domain from the rest of the galaxy. The boundary is a broad region in which solar gravity becomes steadily weaker, while the influence of the Milky Way and passing stars becomes increasingly important. Near the Sun, its gravity clearly controls the motion of planets, asteroids, and smaller bodies. Far away, that control remains present, but it competes with other forces acting across interstellar space. The outer boundary is therefore defined by balance rather than by material. It is a changing gravitational landscape, not a shell that can be crossed at a single exact distance. A useful concept for describing this region is the Hill sphere. A Hill sphere is the approximate volume around one object in which its gravity can hold smaller bodies against the wider pull of a more massive system. For the Sun, the larger system is the Milky Way. The Sun travels through the galaxy while carrying planets and distant debris with it. Close objects remain securely attached to the Sun because its gravity is much stronger than the gentle pull of the galaxy across the same distance. At great distances, the difference between the Sun's attraction and the surrounding galactic forces becomes smaller. The outer limit of stable solar control is often estimated to lie roughly 1 to 2 light-years from the Sun, although the true shape and effective distance vary with direction and with the motion of nearby stars. This region is not spherical in a perfect sense. The gravitational field of the galaxy stretches and compresses it. The Milky Way pulls towards its central regions, while the distribution of matter above and below the galactic disk also contributes a vertical force. Together, these effects create what is called the galactic tide. The term describes the small difference in galactic gravity across the width of the solar system. The tide is extremely weak compared with the forces that govern planetary orbits, but it acts continuously over very long periods. At the solar system's far edge, where the Sun's hold is already faint, this persistent influence can slowly alter the paths of distant bodies. The Sun's outer gravitational region moves with it through the galaxy. It does not remain fixed among the stars. Interstellar gas and dust pass through, and nearby stars follow independent paths. The density of the local galactic environment changes gradually as the Sun travels. In a more crowded region, stellar disturbances become more frequent. In a quieter region, the outer boundary experiences fewer close gravitational encounters. The solar system's edge therefore responds to its surroundings over millions of years. Its overall scale remains immense, but its most weakly held members can be gained, redirected, or lost. Escape from the Sun is not determined by distance alone. A small body can remain bound at a great distance if its speed and direction allow a long orbit around the Sun. Another object at the same distance can escape if it moves too quickly. A bound orbit is one in which the object lacks enough energy to leave the Sun permanently. Near the outer boundary, even a modest disturbance can change that energy. A slight gravitational pull from the galaxy or a passing star can turn an extremely long orbit into an open path leading into interstellar space. The same kind of disturbance can also reduce an object's energy, leaving it more securely attached to the Sun. Because the outer boundary is based on motion and gravity, it cannot be located by observing a change in color, temperature, or composition. Sunlight becomes extraordinarily faint there, but fading light does not define the end of the solar system. The solar wind also forms a large bubble around the Sun, yet that particle-filled region is far smaller than the Sun's full gravitational domain. A spacecraft can leave the main solar wind environment while remaining deeply bound to the Sun. The gravitational solar system extends thousands of times farther than the planetary region, and far beyond the space reached by any human-made object. The passage of time is central to understanding this distant edge. An object near the planets completes an orbit in years, decades, or centuries. Near the outer gravitational boundary, a single orbit can require many millions of years. During that long journey, the galaxy does not stand still around it. Stars change position. Molecular clouds pass at great distances, and the Sun continues along its own galactic path. The object's orbit is therefore exposed to a sequence of weak influences. Most produce only tiny changes, but tiny changes can accumulate when the orbital motion itself is extremely slow. The Sun's mass sets the basic strength of its gravitational reach. Since the Sun contains almost all the mass in the solar system, the planets contribute little to the location of the farthest boundary. Their gravity matters strongly within the planetary region, but at distances approaching a light-year, the solar system behaves mainly as a single mass centered on the Sun. The surrounding galaxy then provides the wider gravitational setting. The result is an outer domain that belongs to the Sun only in a conditional sense. Bodies there are held gently, and their continued attachment depends on the quietness of the environment through which the Sun moves. Astronomers cannot map every object near this boundary directly. Such bodies receive little sunlight and appear extremely faint. Their existence and distribution are inferred from orbital calculations, comet observations, numerical models, and knowledge of how planetary systems form. The estimated limits therefore carry uncertainty. Observations and models indicate that the Sun can retain objects across distances approaching a light year and perhaps farther in favourable orbits. It remains uncertain how densely this remote space is populated, and how its population varies in different directions. The farthest solar system is thus a region of weakening possession. The Sun remains the central gravitational body, but its control is no longer absolute. The galaxy shapes the background, and passing stars briefly add their own pull. No event announces the crossing from one domain into another. A body can spend ages moving through this quiet zone while its orbit slowly changes. At these distances, the solar system blends into the Milky Way through gravity, motion, and time. Beyond the region where the known planets move and far beyond the broad belt of icy worlds near Neptune, the solar system opens into a much larger and more weakly populated space. Here lies the outer Oort cloud, a distant reservoir of small frozen bodies surrounding the Sun in every direction. It is called a cloud because its objects are not arranged mainly in a thin disk. Their paths are believed to form a nearly spherical distribution extending above and below the plane in which the planets travel. No spacecraft has reached this region, and no telescope has directly mapped its population. Its existence is inferred from long-period comets, models of planetary formation, and calculations of long-term gravity. Its inner extent is uncertain, and estimates depend on how astronomers divide the inner and outer parts of the larger cloud. The outer portion may begin at tens of thousands of times the distance between Earth and the Sun. It may continue outward to roughly 100,000 times the distance, approaching about 1.5 light-years from the Sun. Sunlight there is extremely weak. The Sun still appears brighter than other stars to an object bound to it, but it no longer dominates the sky as a broad, warming disk. It is reduced to a brilliant point, and the energy arriving at a frozen surface is only a tiny fraction of that received by Earth. The objects in this remote shell are thought to contain mixtures of water, ice carbon dioxide, ice carbon monoxide, ice methane, ammonia, rocky grains, and dark organic material. Their exact compositions vary because they form from material that passes through different temperatures and chemical environments during the solar system's early history. Most probably remain inactive for immense periods. Their ices stay locked beneath cold surfaces, and their dark crusts change only slowly under cosmic rays and energetic particles. Without strong sunlight, they do not develop the glowing atmosphere and tail associated with an active comet. In the outer cloud, they are quiet nuclei moving through darkness. The outer Oort cloud occupies such an enormous volume that its members are likely separated by vast distances. Even if it contains hundreds of billions or perhaps trillions of objects, the space between neighbouring bodies can remain immense. Estimates of the population and total mass are uncertain, because astronomers observe only the small fraction that enters the planetary region as comets. The cloud may contain material equal to several Earth masses, though models produce a broad range. Its total mass is tiny beside the Sun. The cloud is understood as a surviving product of the solar system's formation. Around 4.5 billion years ago, the young Sun is surrounded by a rotating disk of gas dust ice and growing worlds. Small bodies form across this disk, including in the region occupied by the giant planets. As Jupiter, Saturn, Uranus, and Neptune grow and shift, their gravity scatters many smaller objects. Some are thrown completely away from the Sun and become wanderers in interstellar space. Others are sent into enormous elongated orbits while remaining weakly bound. The gravity of nearby stars in the Sun's birth environment and the tide of the Milky Way gradually change the direction of these stretch paths. Over time, many orbits become tilted far from the original planetary plane, producing the broad spherical cloud. Details of this process remain uncertain. The Sun may be born within a cluster containing hundreds or thousands of other young stars. In that crowded setting, neighbouring stars can affect scattered bodies more strongly than stars do in the Sun's present surroundings. Some material in the cloud may originate around the young Sun, while a smaller fraction may have been captured from the outskirts of other newborn planetary systems. Numerical models indicate that such exchanges are possible during close encounters within a birth cluster. The amount of captured material is not firmly known, and no observed comet has been proven to come from another star's original disk. An object in the outer cloud moves around the Sun with extraordinary slowness. Its path is usually highly elongated, carrying it through a wide range of distances. Near the farthest point of its orbit, its speed relative to the Sun can become very low. A complete circuit may take millions of years. During most of that time, the body remains beyond direct observation, receiving little heat and showing no visible activity. Because the Sun's attraction is faint at such distances, the object responds gradually to the gravity of the Milky Way. The combined pull of the galactic disk and distant stars can alter the orientation and shape of its orbit over long intervals. The word cloud can suggest a soft continuous substance, but the outer Oort cloud contains separate solid bodies within nearly empty space. It has no air mist or shared surface. Its boundary is indistinct. The number of bound objects probably decreases outward, while the ability of the Sun to retain them becomes steadily weaker. Some distant bodies may complete many long orbits. Others may be removed after a gravitational disturbance changes their speed by only a small amount. The cloud is therefore a population in slow exchange with interstellar space, though this exchange is sparse. Direct detection remains beyond present observational ability for ordinary objects there. A small dark body reflects almost no measurable sunlight across such a distance. Even a large world would be difficult to identify unless it retained internal heat or passed in front of a background star. Astronomers instead study the outer cloud through visitors that leave it. Long-period comets arrive from widely scattered directions, supporting the idea of a spherical source. Their incoming paths preserve partial information about their distant orbits, though planets' galactic forces and observational limits complicate the reconstruction. The outer Oort cloud remains the most remote known structural region belonging to the Sun. It contains material from the solar system's earlier stages preserved at temperatures that allow ancient ices to survive. Its bodies are not entirely undisturbed because the galaxy acts continuously upon them, but their surfaces may retain records of chemical conditions older than the planets in their present forms. Across this distant shell, motion is measured in millions of years. Light is reduced to a narrow point, and the Sun holds its smallest companions with a gravity that is real, persistent, and exceedingly gentle. Long before modern astronomy identifies it, a faint stellar system moves through the local space surrounding the Sun. It is known today as Schultz's star after the astronomer who first draws attention to its unusual motion. The system lies in the constellation Monoceros when observed in the present era, but its location on the sky is only one moment in a much longer journey. It does not remain fixed among the background stars. Its true motion carries it away from the solar system, while calculations of that motion trace its path backward toward a much closer encounter in the distant human past. Schultz's star is not a single luminous object. It is a binary system composed of a small red dwarf and a brown dwarf companion. Both are faint. Their combined visible light is weak enough that the system escapes ordinary notice for most of recorded history, even though it passes through the wider solar neighborhood. Its approach is reconstructed from measurements of distance proper motion and radial velocity. Proper motion shows how a star shifts across the sky, while radial velocity reveals how quickly it moves toward or away from the Sun. In the present day, Schultz's star shows only modest sideways movement, but a large speed directed away from the solar system. This combination indicates that much of its path lies along the line between the star and the Sun. When astronomers extend that path backward, the system approaches the Sun rather than circling nearby at a constant distance. The reconstruction places the closest passage roughly 70,000 years ago. The exact date cannot be known with complete precision because every measurement contains uncertainty. Calculations generally place the encounter within a range of several thousand years around that central estimate. At that time, the stellar system moves through a part of space now far behind it. The Sun is also moving through the Milky Way, so the encounter is not the result of one object remaining still while another crosses a fixed boundary. Both systems travel along their own galactic paths. Their separation decreases gradually over many thousands of years, reaches a minimum and then begins to increase again. Nothing in the surrounding space marks the approach. There is no visible frontier around the solar system, and no sudden change in the star's motion. The event unfolds as a quiet adjustment of distance between two moving systems. As Schultz's star draws nearer, it remains an extremely faint source of light. A red dwarf produces energy by fusing hydrogen in its core, but its low mass gives it a cooler surface and a far lower luminosity than the Sun. The brown dwarf companion is dimmer still. It lacks enough mass to sustain the same long-term hydrogen fusion that powers an ordinary star. Together, the pair carries more gravitational influence than their brightness suggests, yet even their total mass remains only a small fraction of the Sun's mass. Their approach, therefore, does not resemble the arrival of a second Sun. It is passage by two low-mass objects whose light is weak and whose gravity becomes important only across the most distant and lightly bound regions of the solar system. The path toward the Sun takes place through interstellar space, the thin region between stars. This space is not empty. It contains sparse atoms, charged particles, dust grains, magnetic fields, and radiation. The density is so low that the stellar system moves through it without anything resembling atmospheric resistance. There's no air to slow the pair, and no medium capable of producing a visible trail. Each component remains bound to the other as the binary travels. Their mutual orbit continues while the center of the pair follows its larger path through the galaxy. The Sun's gravity begins affecting the system from a great distance, but the influence is slight. It gently bends the trajectory into a hyperbolic path, meaning a path that passes once through the Sun's neighborhood and then continues outward rather than remaining in orbit. Because the system arrives with substantial speed relative to the Sun's solar gravity cannot capture it. During the approach, the separation between the two objects remains tiny compared with their distance from the Sun. From the perspective of the solar system's outermost region, the binary largely behaves as one passing source of gravity. Small differences caused by the individual components exist, but the broad encounter is governed by their combined mass, their speed, and the distance of closest approach. The faster a star passes, the less time its gravity has to alter nearby objects. The farther away it remains, the weaker the effect becomes. Schultz's star approaches closely by stellar standards, yet it does not come near the planetary system. Its course leads toward the remote gravitational outskirts, where bodies move slowly and the sun holds them only gently. The ancient sky contains no instrument capable of measuring this movement. Human beings living at the time observed bright stars, the moon, the planets, and the changing band of the Milky Way. But Schultz's star is too faint to become a clear new point of light under ordinary conditions. Red dwarfs can sometimes produce flares, brief releases of energy caused by magnetic activity. Schultz's star may have flared during its passage as similar stars do, but no evidence records a particular outburst at that time. It remains uncertain whether any flare becomes bright enough to be noticed from Earth. The established finding concerns the system's motion and distance, not a witnessed appearance in the prehistoric sky. The approach is known only because modern observations allow motion to be unfolded backward through time. Infrared surveys reveal the system's cool, faint nature. Spectroscopic measurements determine its speed along the line of sight. Astrometric measurements refine its distance and sideways movement. These observations are combined with models of motion through the local galactic environment. The resulting path is a probability range rather than a perfectly thin line. Different measurements produce slightly different versions of the encounter, but they agree that the system once travels far closer to the Sun than it does today. The event remains physically quiet, visually obscure, and entirely natural. A faint binary drifts inward from interstellar space, crosses the Sun's remote neighborhood, and continues on, leaving its presence to be reconstructed tens of thousands of years later. Schultz's star travels through the galaxy as a compact binary system, with two low-mass bodies held together by their mutual gravity. The brighter member is a very small red dwarf, while the dimmer companion is a brown dwarf. They are separated by a distance comparable to the scale of the inner planetary system, yet from far away they appear almost blended into a single point. Their shared motion across the Milky Way carries both objects together, while each follows an orbit around the center of mass between them. This center is the balance point set by their unequal masses. It lies closer to the heavier red dwarf, though neither body remains completely still. Both circle the same invisible point as the pair moves through interstellar space. The primary belongs to the coolest end of the ordinary stellar sequence. Astronomers classify it near spectral type M 9.5, a label, based on the pattern of light produced by its atmosphere. An M-type star is a red dwarf with a lower surface temperature and much less mass than the Sun. Schultz's star lies close to the lower mass limit at which sustained hydrogen fusion can continue. Its measured mass is about 99 times the mass of Jupiter, equal to roughly 1/10 of the Sun's mass. The exact border between a star and a brown dwarf depends slightly on composition age and the physical models used, but the primary remains massive enough to behave as a true star. Deep within it, hydrogen nuclei combine slowly and release energy. The rate is modest, allowing such a star to remain active for far longer than the present age of the universe. The small mass compresses the primary less strongly than the Sun, and its interior transports energy mainly through convection. Convection is the movement of warmer material upward and cooler material downward. This circulation can extend through nearly the entire star. It mixes the available hydrogen efficiently and gives red dwarfs exceptionally long lives. The star's outer layers remain cool enough for molecules to survive, producing a complicated spectrum filled with broad absorption bands. Much of its energy emerges at red and infrared wavelengths. Its visible light is therefore faint, even though it continues to generate energy through fusion. At its present distance, it requires telescopes to be studied clearly, and its low position near the crowded band of the Milky Way once makes it easier to overlook among many background sources. The companion belongs to spectral type T5.5. T-type brown dwarfs are cool substellar objects whose infrared spectra often show strong absorption by methane and water vapor. Substellar means that an object forms in a star-like way, but lacks enough mass for stable hydrogen fusion. The companion has a measured mass near 66 times that of Jupiter. This places it below the usual hydrogen-burning boundary but above many lighter brown dwarfs. Early in its history, it possesses heat from formation and from gravitational contraction. It may also burn a limited supply of deuterium, a heavy form of hydrogen, during an early stage. That process does not last. Without sustained hydrogen fusion, the brown dwarf gradually cools and fades as it ages. The companion's present temperature is estimated at about 1,250 kelvins. At this temperature, it gives off most of its radiation in the infrared. To human eyes, it would not resemble a bright star. Its atmosphere contains clouds and gases shaped by temperature, gravity, and chemical reactions. Methane becomes an important absorber, while water vapor also leaves strong marks in the spectrum. The object is more massive than most planets, but mass alone does not make it a star. Its central pressure and temperature remain insufficient for ordinary hydrogen fusion. The distinction rests on internal physics rather than on appearance size or the manner in which the object is named. The two bodies complete an orbit in a little more than 8 years. Their path is moderately eccentric, meaning that the distance between them changes during each circuit rather than remaining constant. The orbit is also viewed from Earth at a steep angle, allowing observations over time to reveal the shifting positions of the components. High-resolution imaging separates the dim companion from the brighter primary, while repeated astrometric measurements follow their movement. Astrometry is the precise measurement of position. By combining the apparent orbit with the distance to the system, astronomers determine the true scale of the binary and calculate the masses of both members through gravity. These dynamical masses depend on orbital motion rather than only on estimates from brightness or temperature. The red dwarf is magnetically active. Its moving, electrically charged interior creates magnetic fields that can store and release energy. Observations detect variable emission and occasional flaring along with radioactivity. A flare briefly increases the star's output, as magnetic energy heats part of its atmosphere. Such activity is common among many cool red dwarfs, especially those rotating fast enough to maintain strong magnetic processes. The presence of flares does not make the system steadily bright. Most of the time, the primary remains a weak source, and the brown dwarf remains much fainter. A brief outburst changes the light temporarily, but does not transform the pair into a lasting object of naked eye brightness at ordinary stellar distances. The binary's motion relative to the Sun is unusual in its direction. Its sideways drift across the sky is modest, compared with its strong motion along the line of sight. Spectral measurements show that the system is now receding rapidly at more than 80 kilometers per second. A shift in the wavelengths of features within its spectrum reveals this radial motion. Because much of the velocity points away from the Sun, the pair can appear to move only slowly against background stars, even while traveling quickly through space. This geometry helps explain why its importance is not recognized from proper motion alone. Both members are old objects belonging to the Milky Way's disk population. Their masses, temperatures, activity and motion provide separate clues to their history, though no single measurement gives an exact age. The massive but cool brown dwarf indicates that the system has existed for billions of years, allowing the companion time to lose much of its original heat. The pair remains securely bound despite its fast journey through the galaxy. Across every year of that journey, the red dwarf and brown dwarf continue their compact orbit, carrying one another through darkness as a single gravitational system whose faint light conceals the weight and complexity within it. The closest passage of Schultz's star occurs at a distance that is small by stellar standards and still enormous by planetary standards. Modern calculations place the binary roughly 50,000 astronomical units from the Sun at minimum separation. 1 astronomical unit is the average distance between Earth and the Sun. At about 50,000 such units, the passing system remains nearly 8/10 of a light-year away. Light itself takes many months to cross that gap. Neptune, by comparison, travels only about 30 astronomical units from the Sun. The star therefore passes more than 1,000 times farther away than Neptune outside every known planet and far beyond the region usually shown in diagrams of the solar system. Its path belongs to the remote domain where the Sun's most weakly bound objects are expected to move. The time of closest approach is estimated at roughly 70,000 years before the present. Different studies produce somewhat different central values because they use different measurements, galactic models, and statistical methods. Some place the encounter several thousand years earlier or later than this estimate. The range does not indicate that the passage itself is doubtful. It reflects the limits of tracing a faint moving system backward through tens of thousands of years. The main conclusion remains stable. Schultz's star passes unusually close to the Sun during the period when early modern humans and other human populations live on Earth, and the event occurs far beyond any written record. The distance is reconstructed rather than directly observed. Astronomers begin with the system's present position, its distance from the Sun, its motion across the sky, and its velocity along the line of sight. These measurements describe a moving point in three-dimensional space. The binary's internal orbit must also be considered because the observed light and position can shift slightly as the two bodies circle their shared center of mass. Once the motion of the center of the system is determined, a model carries that motion backward through the gravitational field of the Milky Way. The Sun's own galactic motion is included as well. The calculation then identifies the time when the separation between the two systems reaches its smallest value. Uncertainty enters at every stage. A small error in distance changes the inferred position. A small error in radial velocity changes how rapidly the star moves along the line between it and the Sun. Proper motion uncertainty changes the sideways component. Over 70,000 years, these small differences widen the possible path. Astronomers therefore do not describe the encounter with one perfectly exact point. They calculate a distribution of possible trajectories, each consistent with the measurements within their uncertainties. Most of those trajectories place the binary within the broad region, assigned to the outer Oort cloud. A smaller number place it somewhat farther away or somewhat closer. The most likely paths cluster near the same general distance. The outer Oort cloud has no directly observed outer wall, so saying that the star enters it depends partly on how that region is defined. Many models extend the cloud outward to about 100,000 astronomical units, while others use a smaller effective limit because objects near the extreme edge are only weakly attached to the Sun. With an estimated closest distance near 50,000 astronomical units, Schultz's star passes inside many standard models of the cloud. It does not pass through a dense band of visible bodies. The cloud is a vast volume of almost empty space, and its members are probably separated by distances that can exceed those between planets. The phrase passing through the cloud describes location within this remote population, not contact with a continuous substance. The binary approaches on an open trajectory. Its speed relative to the Sun is high enough that solar gravity bends the path only slightly and cannot capture the system. Near closest approach, it moves at more than 80 kilometers per second relative to the Sun. At that speed, it crosses a distance equal to Earth's orbit in only a few weeks. Crossing the much larger outer cloud region still takes thousands of years, but the time spent near the minimum distance is short compared with the millions of years required for many distant cloud objects to orbit the Sun. The encounter is therefore a passing event rather than a long residence. The pair's combined mass also helps define the encounter. The red dwarf and brown dwarf together contain well under 1/5 of the Sun's mass. Their gravity is real but far weaker than that of the Sun at equal distance. During closest approach, the binary remains so far away that the Sun continues to dominate all known planets without meaningful competition. There is no point at which Earth, the giant planets, or the Kuiper belt lies between two comparable stellar pools. The geometry remains strongly centered on the Sun. Only the extreme outer region places small bodies at distances where a passing low-mass system becomes locally relevant. The closest approach is not a collision and does not resemble one. The stars themselves remain separated from the Sun by trillions of kilometers. Their own binary orbit continues throughout the passage, and neither component comes close to another star. The encounter is best understood as two gravitational systems moving past one another through a shared region of galactic space. Each carries its bound material and each follows a path shaped mainly by its previous motion. The Sun briefly gains a nearby stellar neighbor, then the distance begins to increase again. No physical marker records the exact instant of minimum separation. The binary does not cross a glowing boundary, and the outer Oort cloud does not brighten around it. The moment exists as a point in a calculated curve of distance against time. Before that point, the separation decreases. After it, the separation grows. Modern measurements reveal the curve only indirectly, yet the agreement among position, velocity, and orbital models makes the passage one of the best-known close stellar encounters in the recent history of the solar system. Its importance rests not on visual drama, but on scale. A faint binary reaches the remote outskirts of the Sun's domain, passes through a region measured in tens of thousands of astronomical units, and continues outward without ever entering the planetary system. Across the outer Oort cloud, the passage of Schultz's star adds a temporary source of gravity to a region where motion is already slow and loosely controlled. The Sun remains the dominant mass, but its pull on the most distant bodies is extremely weak. An icy object tens of thousands of astronomical units away can take millions of years to complete one orbit. Near the farthest part of that path, its speed may fall to only a small value compared with the motion of planets. A passing star does not need to come near the object physically to alter such a delicate orbit. Its gravity acts across space, changing the object's velocity by a slight amount. The change is usually too small to notice in a single moment. Yet the future path can differ greatly because the original orbit is so large and slow. The strength of the disturbance depends first on distance. Gravity weakens rapidly as separation increases, so an object passing relatively near the binary feels a stronger pull than an object on the far side of the cloud. The direction of that pull also matters. If the passing star draws an object partly along its existing motion, the object gains orbital energy around the Sun. If the pull acts against the motion, the object loses energy. A sideways pull changes the direction of travel and can tilt the orbital plane. These changes combine in different ways across the cloud because the bodies occupy many positions and follow many orientations. The encounter, therefore, does not move the entire outer cloud as one structure. It produces a scattered pattern of small disturbances. The speed of Schultz's star limits the duration of its influence. The binary travels past the Sun at more than 80 kilometers per second, so it does not remain close to any one part of the cloud for long on astronomical timescales. A slower star of the same mass and at the same distance would act for a longer interval and could produce a larger cumulative effect. A more massive star would also create stronger changes. Schultz's star combines a relatively low total mass with a high passing speed. Its close approach is notable, but these other properties keep the disturbance modest. Numerical models indicate that the planetary system remains unaffected and that most outer cloud objects continue along orbits that differ only slightly from their previous paths. A useful way to describe a fast encounter is the impulse approximation. This term means that the passing object changes a body's velocity during a period short compared with the body's own orbital time. An outer cloud object may need millions of years to circle the Sun, while the strongest part of the stellar passage lasts only a small fraction of that interval. The body barely moves along its enormous orbit while the binary passes. It instead receives a gentle gravitational impulse, after which it continues on a somewhat altered path. The impulse is not a collision or a sudden mechanical strike. It is the accumulated result of gravity acting continuously, as the distance first decreases and then increases. The Sun also responds to the passing binary. Schultz's star pulls on the Sun as well as on every distant object. What changes an orbit is not the star's absolute pull alone, but the difference between the pull on the object and the pull on the Sun. This difference is called a tidal effect. If the binary attracts both almost equally, their relative motion changes very little. If it is noticeably closer to one than to the other, the unequal attraction becomes more important. Because the outer cloud spans an immense volume, this tidal difference varies across it. Bodies on the side nearest the passing system receive a different impulse from bodies located closer to the Sun or on the opposite side. Some disturbed objects can move into orbits with slightly smaller closest distances to the Sun. Others can be lifted into wider paths or removed from the solar system entirely. Ejection occurs when an object gains enough energy to escape the Sun's gravity. At the outer edge, the amount of added speed required can be very small because the object is already weakly bound. Even so, the sparse population and the limited strength of the encounter mean that only a small fraction is expected to experience a major change. The majority remain attached to the Sun. A few may shift into paths that become important much later, after travelling inward or outward over extremely long intervals. The timing of any inward journey separates the gravitational event from a possible visible comet. An object disturbed at 50,000 astronomical units does not fall rapidly toward the Sun. Its new orbit still covers an enormous distance, and the motion begins from a region where solar gravity produces slow acceleration. Travel toward the planetary system can take hundreds of thousands or millions of years. There is therefore no expectation of an immediate comet display following the stellar passage. The encounter changes orbital possibilities rather than producing a sudden wave. Each affected body follows its own schedule according to its position, velocity, and altered orbit. The Milky Way's tide continues to act before, during, and after the encounter. Schultz's star adds a temporary disturbance to this persistent background. In some cases, the stellar pull and the galactic tide act in similar directions. In others, they oppose one another. Later passages by other stars can modify the same orbits again. This makes it difficult to connect any single distant object uniquely to one encounter. An orbit observed near the Sun today may preserve part of an older disturbance, but it also carries the effects of planetary gravity, galactic tides, and other stellar passages. Computer simulations explore the encounter by creating many possible outer cloud objects and calculating how they respond to many possible paths of Schultz's star. Because the cloud itself is not directly mapped, these models begin with assumed distributions based on solar system formation and long-period comet observations. The results indicate a weak but structured disturbance strongest among the most distant and least tightly bound members. Exact numbers remain uncertain because the star's past trajectory has a range of possible values and the original cloud population is unknown. The broad physical picture is clearer. Across the remote shell of ice, a passing low-mass binary changes some velocities slightly, leaves most bodies nearly undisturbed, and allows gravity to carry those small differences forward through immense spans of time. The possible memory of Schultz's star does not appear as a mark on a planet or as a visible scar across space. It is sought instead in the directions and shapes of cometary orbits. Long-period comets arrive from the distant solar system on paths that can take hundreds of thousands or millions of years to complete. When one of these bodies enters the region where telescopes can detect it, its present motion allows astronomers to calculate an incoming trajectory. That trajectory points back toward a direction in the sky. The direction is called the radiant, meaning the apparent point from which the body approaches. A radiant does not necessarily identify the exact place where the object forms. It records the direction of its recent inbound motion after gravity has altered the path over a long journey. If distant comets enter the inner solar system through completely unrelated disturbances, their radiance may be expected to spread broadly across the sky, though the distribution is never perfectly uniform. The Milky Way's tide creates preferred patterns. The Sun's movement through nearby space also affects which directions are sampled. Planetary encounters can reshape orbits after comets arrive, and observational surveys examine some parts of the sky more thoroughly than others. A passing star can add another pattern. Its gravity acts most strongly on objects lying in particular positions relative to its path, so a group of disturbed bodies can begin inward journeys with related directions. After a long delay, some may appear as a loose concentration of radiance rather than as a narrow stream. Astronomers search for such a concentration among objects travelling on nearly parabolic or hyperbolic paths. A parabolic path lies near the boundary between a closed orbit and escape. A hyperbolic path is formally open, allowing an object to leave the Sun permanently. Some hyperbolic objects come from interstellar space, but a slightly hyperbolic orbit does not prove an interstellar origin. The gravity of planets can accelerate a solar system comet and place it on an escaping path. Uncertainty in the measured orbit can also make a nearly parabolic body appear weakly hyperbolic. Galactic tides and stellar encounters may alter distant comets before they approach the planets. Each possibility must be considered before an incoming direction is treated as evidence of a past flyby. A statistical study of known hyperbolic minor bodies identifies an excess of high-speed radiance in a region of the sky toward Gemini. The concentration lies away from the directions expected simply from the Sun's motion through the local stellar population. Several of the objects within it are regarded as new or returning Oort cloud comets, rather than confirmed visitors from another planetary system. When the reconstructed path of Schultz's star is compared with this pattern, the encounter offers a possible explanation. The geometry suggests that the binary's ancient gravitational passage may help send some outer cloud bodies onto paths whose incoming directions later collect in the observed region. The word possible remains essential. The number of suitable objects is limited and the catalogue is shaped by discovery conditions. Comets are easier to find when they bright and strongly pass near the Sun approach at favourable angles, or enter areas watched by active surveys. faint objects with distant closest approaches often escape detection. Observations made over a few centuries sample only a tiny part of a process unfolding across millions of years. A small concentration can become stronger or weaker as more objects are discovered and as existing orbits are refined. Statistical significance shows that a pattern is unlikely to arise randomly within the assumptions of an analysis. It does not by itself establish one physical cause. The long travel time creates another difficulty. Schultz's star passes the solar system roughly 70,000 years ago, but many objects disturbed in the outer Oort cloud require much longer than this to reach the region of the planets. Bodies that appear now may have occupied favourable positions during the encounter, or may have experienced only part of their inward change from the star. Others can respond mainly to the continuing galactic tide. Some objects affected more strongly may not arrive for hundreds of thousands of years. The observed sample therefore does not represent the complete result of the flyby. It is a narrow view of motions whose timing depends on the original orbit of every body. Orbital reconstruction also becomes less certain when traced far from the Sun. Near the planets, positions and speeds can be measured with precision. Far beyond them, the path must be calculated through weak forces acting over long periods. The gravity of the giant planets is included along with the galactic tide and known stellar encounters. Unknown or poorly measured encounters may also matter. Small changes in a comet's observed motion can produce large differences in its calculated position near the outer cloud. Non-gravitational forces add further uncertainty when sunlight warms an active comet, and escaping gas acts like a weak thruster. These effects are usually small, but they can influence a delicate reconstruction. No individual known comet carries a secure label connecting it to Schultz's star. A convincing identification would require an accurately measured orbit, a reliable model of the encounter, and a backward path placing the comet in a position where the binary's gravity produces the necessary change. Even then, the galactic tide and other stars could create similar outcomes. The strongest claim supported by present work is therefore collective rather than individual. A group of incoming directions shows a pattern consistent with a stellar disturbance, and Schultz's star is a plausible source because its passage is both close and recent on the timescale of outer cloud motion. This possible imprint does not imply a large comet shower. The binary is low in mass and moves rapidly, limiting the strength of its disturbance. Most cloud objects remain almost unchanged, and models of the encounter predict little alteration in the overall flow of long-period comets. A subtle directional excess can exist without a dramatic increase in their number. The orbital record, if it truly contains the passage, resembles a faint alignment rather than a sudden flood. It rests within the geometry of a small sample preserved through slow travel and recovered through measurements made long after the star has departed. Deeper within the distant reservoir of the solar system lies a more tightly bound population often called the inner Oort cloud. Unlike the outer cloud, which may extend nearly to the limit of the Sun's gravitational control, this inner region occupies distances where solar gravity remains weak but more secure. Its exact boundaries are uncertain because no direct image reveals its shape or density. Many models place it between several thousand and several tens of thousands of astronomical units from the Sun. The transition from the inner cloud to the outer cloud is gradual. The important distinction is the increasing strength with which the Sun holds objects as distance decreases. The inner Oort cloud is expected to contain icy bodies scattered outward during the early formation of the planetary system. As the giant planets grow, their gravity sends small objects onto highly elongated paths. Some escape entirely. Others remain bound with orbits that carry them far beyond the planets. In the crowded environment where the Sun probably forms nearby stars and the gravity of the surrounding birth cluster help raise the distant ends of these orbits. This process can detach objects from repeated close encounters with Jupiter and Saturn. Once their closest points move beyond the giant planets, the bodies can survive for billions of years in a remote storehouse. The inner cloud may therefore preserve much of the material scattered during the solar system's youth. Its overall shape is likely broad and thick, though perhaps less perfectly spherical than the outer cloud. Objects closer to its inner edge can retain some memory of the flat disk from which they originate. Their orbits may show preferred inclinations rather than complete randomness. Farther outward, stellar encounters and the tide of the Milky Way can gradually spread the orbital planes more widely. Numerical models produce different structures depending on the density of the Sun's birth environment, the arrangement of the early giant planets, and the timing of their migration. Observations indicate that a detached inner population should exist, but its total number, mass, and precise geometry remain uncertain. The bodies within this region move slowly, but their orbits are shorter than those of objects near the outer boundary. A complete journey around the Sun can still take hundreds of thousands or millions of years. At the distant end of an orbit, sunlight is only a faint point of energy, and surface temperatures remain extremely low. Water ice, methane, carbon monoxide, and other frozen compounds can survive with little change from solar heating. Impacts are probably rare because the population is spread through an enormous volume. Each object spends most of its existence in isolation, following a path shaped by the Sun and by weak external forces. Schultz's star exerts less influence here than it does in the outer cloud. The reason begins with distance. At closest approach, the binary remains roughly 50,000 astronomical units from the Sun. An object in the inner cloud is therefore generally farther from the passing system than some bodies in the outer cloud, and is held more strongly by the Sun. The star pulls on both the Sun and the object, but the difference between those pulls becomes smaller across the more compact inner region. This difference is the tidal disturbance that changes the object's orbit around the Sun. Since the Sun's binding force grows, as distance decreases, the same passing star produces a smaller relative change. The high speed and low mass of the binary further reduce its effect. Schultz's star does not remain near the inner cloud for long, and its combined mass is much less than that of the Sun. Computer models therefore show that only a very small number of inner cloud objects experience meaningful changes. Most continue on nearly the same orbits after the passage. Their distances and orbital planes may shift slightly, but these differences remain small beside the scale of their original paths. The encounter does not compress the cloud, tear it apart, or send a broad population inward. The inner cloud can also act as a long-lived source that replenishes the outer cloud. Over billions of years, galactic tides and repeated stellar passages slowly transfer some bodies between orbital zones. An object can move outward into a more weakly bound path where later disturbances become stronger. Another can shift inward and become more resistant to removal. This exchange is gradual and irregular. The inner population survives because it is protected from both major planetary scattering and the strongest external disturbances. It occupies a middle domain distant enough to avoid frequent contact with the giant planets, yet close enough to remain securely attached to the Sun. A few observed bodies provide possible hints of this region. Sedna is one example. It travels on a highly elongated orbit whose nearest point remains far beyond Neptune. Its distant point reaches close to 1,000 astronomical units, still well inside the distances commonly assigned to the inner Oort cloud. Other detached objects follow similarly unusual paths. They do not directly reveal the inner cloud, but they show that the solar system contains bodies separated from ordinary interaction with Neptune. Their existence supports the idea that early stellar encounters, planetary migration, or other ancient processes place objects into remote protected paths. It remains uncertain which mechanism dominates for each known body. Direct observation of the inner cloud itself remains extremely difficult. At thousands of astronomical units, even a large icy world reflects almost no sunlight toward Earth. Surveys can discover an object only if its orbit brings it much closer, or if it is unusually large and bright. Estimates therefore rely heavily on formation models and on the number of long-period comets reaching the inner solar system. The hidden population may be larger than that of the outer cloud, because stronger solar binding allows more bodies to survive. Its total mass could exceed the mass of the outer reservoir, though current evidence does not determine a precise value. Within this deeper region, the ancient stellar passage becomes a faint gravitational event. The binary crosses the remote surroundings of the Sun, but the inner cloud remains largely stable. Its bodies continue their immense orbits under a solar pull that is weak by planetary standards and still strong enough to preserve them. Across hundreds of thousands of years, their motion changes slowly, carrying records of the solar system's early scattering history more clearly than records of one brief passing star. Closer to the Sun than the inner Oort cloud lies the scattered disk, a broad population of icy bodies whose orbits extend well beyond Neptune. This region is not a smooth ring and does not possess a sharp inner or outer edge. Its members occupy elongated, tilted, and often unstable paths created by repeated gravitational encounters with the outermost giant planet. The scattered disk begins near the neighborhood of Neptune and reaches outward for hundreds of astronomical units. Some objects travel much farther at the distant ends of their orbits, but their histories remain tied to the planetary region, because Neptune continues to shape their motion over long periods. The word scattered describes the origin of these orbits. During the formation and early rearrangement of the outer solar system, Neptune exchanges energy and angular momentum with smaller bodies. Angular momentum is a measure of orbital motion that depends on mass, speed, and distance from the center of the orbit. A close encounter can increase a small body's orbital energy, lifting its farthest point away from the Sun. Another encounter can reduce that energy or change the direction of the orbit. Across many passages, objects spread into a wide range of inclinations and eccentricities. Eccentricity describes how strongly an orbit differs from a circle. Many scattered disk objects follow highly eccentric paths, approaching Neptune's region at one end and moving into much darker space at the other. Neptune remains the main controlling influence because many of these bodies return close enough for its gravity to act again. They do not usually pass close to the planet on every orbit. Resonances, which are repeated gravitational relationships between orbital periods, can delay or redirect encounters. A body may complete a certain number of circuits while Neptune completes another regular number, allowing small pulls to accumulate in a patterned way. Some resonances provide temporary protection by keeping the object away from Neptune at the most dangerous parts of its path. Others allow the orbit to change gradually until a closer meeting becomes possible. The scattered disk is therefore dynamic. Its population shifts slowly as bodies move between stable temporary and escaping paths. The best-known large member is Eris, a dwarf planet whose orbit is both distant and inclined. Eris travels around the Sun in more than 500 years, moving from roughly 38 astronomical units at its nearest point to nearly 100 astronomical units at its farthest. Its path rises well above the main planetary plane. Other large scattered objects include Gong Gong and smaller bodies with similarly stretched orbits. Their surfaces contain water ice, methane, and other frozen compounds, though composition differs from object to object. Sunlight is weak across most of their paths, and temperatures remain low enough for volatile ices to survive. When some smaller members move closer to the Sun, heating can release gas and dust, turning them into active comets. The scattered disk is regarded as a major source of short-period comets, especially those associated with the gravitational control of Jupiter. A scattered object can undergo a sequence of encounters that moves its nearest point inward. Neptune begins the process, then Uranus and Saturn can alter the orbit, and Jupiter can finally place the body on a much shorter path. Such an object becomes a centaur while it moves among the giant planets. Centaurs are small bodies on unstable orbits that cross or approach the paths of one or more giant planets. Their lifetimes in this region are usually brief on the scale of the solar system, because repeated encounters eventually send them inward, outward, or completely away. Not every distant object with an elongated orbit belongs to the scattered disk. Classification depends mainly on whether Neptune can still exert strong long-term control. Some bodies have closest points too far from Neptune for ordinary encounters. These are often called detached objects. Their orbits may preserve the effects of early planetary migration, ancient stellar passages, or other processes that separate them from Neptune. The boundary between scattered and detached populations is not always exact. Numerical integrations which calculate motion across long spans of time help determine whether a particular orbit remains connected to the planet. Small uncertainties in measured positions can sometimes lead to different classifications. Schultz's star produces no known major rearrangement in this region. At closest approach, the binary remains tens of thousands of astronomical units away, while scattered disk objects remain mostly within a few hundred astronomical units of the Sun. The difference in scale is immense. Solar gravity holds these bodies far more strongly than it holds members of the outer Oort cloud. Neptune also supplies a local gravitational influence that is many times more important than the distant passing star. The pull of Schultz's star on the Sun and on a scattered object is almost the same, because their separation from one another is tiny, compared with their shared distance from the binary. The resulting tidal difference is therefore exceedingly small. Computer models of close stellar encounters confirm this contrast. A passage capable of noticeably altering the scattered disk would need to be much closer, much slower, or far more massive. Schultz's star is low in mass and moves rapidly. Its trajectory through the outermost solar domain changes the motion of only the most weakly bound bodies by meaningful amounts. In the scattered disk, any gravitational impulse is buried beneath the normal influence of the Sun and Neptune. No observed orbital pattern among its members requires the passage as an explanation. The region still carries records of older events. Neptune's migration during the early solar system leaves resonant structures and scattered paths. Encounters among growing planets and smaller bodies remove much of the original material. Collisions change surfaces and occasionally produce fragments. Over billions of years, the surviving population becomes a thin remnant of a once larger disk. Its present form reflects internal planetary history, rather than the recent passage of a faint star. Across the scattered disk, icy bodies continue to follow long sloping orbits through weak sunlight. They return again and again toward Neptune's gravitational reach, where small changes accumulate over immense intervals. Their motion is restless compared with the protected objects farther away, yet it remains firmly centered on the Sun and shaped by the outer planet that first scattered them. Closer to the Sun than the scattered disk lies the Kuiper Belt, a broad ring of frozen worlds extending beyond Neptune. It occupies the outer part of the planetary system beginning near 30 astronomical units from the Sun and thinning beyond roughly 50 astronomical units. Its shape is flattened because most of its members travel near the same general plane as the planets. The belt is not a crowded band of closely packed objects. It is an immense region of darkness in which each known body is separated from its neighbours by vast distances. Sunlight reaches these objects only as a weak glow, yet it remains strong enough for telescopes to detect the largest surfaces through reflected light. The Kuiper belt forms from material left behind after the planets take shape. In the young solar system, a wide disk of ice and rock surrounds the Sun beyond the growing giant planets. Much of this material is later removed. Neptune scatters some bodies outward, captures others into resonances, and sends many away from the solar system. The surviving belt contains only a small fraction of its original mass. Numerical models indicate that the early outer disk may hold tens of Earth masses, while the modern Kuiper belt contains far less than one Earth mass. The exact loss depends on how Neptune migrates and how the giant planets rearrange their orbits. Astronomers divide the belt into several overlapping populations according to orbital behavior. The classical Kuiper belt contains bodies that avoid strong present-day encounters with Neptune and remain outside its main scattering influence. Some follow relatively circular and gently tilted orbits. These are often called the cold classical population, where cold refers to low orbital excitement rather than surface temperature. Others travel on more tilted and elongated paths and are called the hot classical population. Their different colors, sizes, binary frequencies, and orbital distributions suggest that they do not all form in the same place. The cold group may preserve material that forms near its present location, while many hot classical objects may migrate outward from regions close to the Sun. Resonant objects occupy another important part of the belt. A resonance occurs when the orbital periods of two bodies form a repeated numerical relationship. Pluto, the best-known resonant object, completes 2 orbits for every 3 completed by Neptune. This pattern prevents close encounters because the 2 worlds return to their relative positions in an orderly way. Pluto crosses inside Neptune's average orbital distance, but the resonance keeps the planets safely separated. Many smaller bodies share the same relationship and are called plutinos. Other objects occupy different resonances, revealing how Neptune's slow outward migration captures bodies and carries them into stable patterns. Pluto is one of several dwarf planets in the outer solar system. It possesses a rocky and icy interior, a surface rich in nitrogen, methane, and carbon monoxide ice, and a thin atmosphere that changes as its distance from the Sun varies. Its large moon, Charon, is more than half Pluto's diameter, making the pair unusually close in size. Haumea, another dwarf planet, rotates rapidly and has an elongated shape. Makemake shows methane ice on its surface. Smaller Kuiper belt bodies display a wide range of colors from neutral gray to deep red. These colors arise from differences in composition, surface processing impacts, and radiation, acting on carbon-rich ices over billions of years. Many objects in the belt possess moons, and some exist as nearly equal pairs. The cold classical population contains an especially high fraction of wide binaries. These fragile systems can survive only if they avoid strong gravitational encounters. Their continued existence supports the view that part of the belt remains relatively undisturbed since the early solar system. Collisions still occur, though they are uncommon in the present sparse population. Some collisions break objects apart and create families of fragments with related orbits and surface compositions. The Haumea family is a likely example, with members showing unusually pure water ice. The belt also supplies some bodies that later become centaurs and short-period comets. Slow orbital changes can move an object toward Neptune, where repeated encounters begin a journey among the giant planets. When such a body approaches the Sun closely enough, buried ice can turn directly into gas. Dust escapes with the gas and forms a surrounding cloud and tail. Most Kuiper Belt objects never become active comets. They remain frozen and distant, preserving materials from the outer protoplanetary disk. Schultz's star has no measurable effect on the structure of the Kuiper Belt. At closest approach, the binary remains about 50,000 astronomical units from the Sun, while the belt lies within only a few dozen astronomical units. Across such a compact region, the passing star pulls almost equally on the Sun and on every Kuiper Belt body. The small difference between these pulls produces a tidal force far weaker than the gravity of the Sun and Neptune. The star's low mass and high speed reduce the disturbance further. Its passage cannot shift Pluto from resonance tilt, the classical belt separate binaries, or create the observed populations. The current architecture of the Kuiper Belt instead records events from the solar system's early development. Neptune's migration explains many resonances. The separation between cold and hot populations reflects different formation zones and histories. The belt's low total mass points to extensive removal. Sharp orbital boundaries and concentrations provide tests for models of planetary movement. Some details remain unsettled, including the exact path followed by Neptune and the possible role of additional planets that may once have existed among the giant worlds. Observations continue to refine the number sizes and colors of distant objects, but no feature requires a recent stellar flyby. Within the Kuiper Belt, the Sun remains an overwhelming gravitational center. Neptune shapes the edges in resonant patterns, while collisions and radiation slowly alter surfaces. Schultz's star passes too far away to disturb this ordered region. The belt continues as a thin ancient ring of ice and rock, carrying the quiet record of planetary formation rather than the imprint of the faint binary beyond it. Inside the distant belts of ice, the Sun surrounds itself with a vast bubble of moving particles and magnetic fields called the heliosphere. This region forms because the Sun continually releases the solar wind, a thin flow of charged particles that streams outward from the hot outer atmosphere. Most of the wind consists of protons and electrons with smaller amounts of heavier atomic nuclei. Near Earth, it passes at hundreds of kilometers per second. As it travels outward, the flow spreads through an ever larger volume and becomes steadily thinner, yet it continues carrying the Sun's magnetic field far beyond the planets. The heliosphere is therefore not a solid shell. It is a changing region created by the meeting of the solar wind with the gas and magnetic field between the stars. The Sun moves through a local cloud of interstellar material composed mainly of hydrogen and helium. This material is exceedingly sparse, but the solar wind is sparse as well at great distances. Their interaction produces a broad boundary whose position changes with solar activity and with conditions in surrounding space. The heliosphere is often compared with a bubble, though its true shape is more complicated. Motion through the interstellar medium presses on the side facing the Sun's direction of travel and stretches the region behind. Magnetic fields, particle pressure, and the changing strength of the solar wind all influence the form. Observations and models indicate that the boundary is not a simple sphere and may shift by several astronomical units over time. The first major transition is the termination shock. A shock is a region where a flowing gas or plasma slows abruptly and changes temperature and density. Plasma is matter in which atoms are separated into charged particles. Before reaching the termination shock, the solar wind travels faster than waves can move through the plasma. At the shock, it slows below that characteristic speed and becomes hotter and denser. Voyager 2 crosses this boundary at roughly 84 astronomical units from the Sun, while Voyager 1 crosses it near 94 astronomical units. The difference shows that the heliosphere is uneven and that its boundary moves. The two spacecraft also pass through at different times and in different directions, so they sample separate parts of a living structure. Beyond the termination shock lies the heliosheath. Here the slowed solar wind continues outward while interacting more strongly with interstellar material. The region contains turbulent magnetic fields, energetic particles, and flows that are less orderly than the wind closer to the Sun. Its thickness varies with direction. Voyager 1 travels through the heliosheath for several years before reaching its outer limit, and Voyager 2 follows a different path through a region of different width. The heliosheath is not empty space between two neat surfaces. It is a broad transition zone in which the character of the plasma changes gradually and irregularly. The outer edge of the heliosphere is called the heliopause. At this boundary, pressure from the solar wind balances pressure from the surrounding interstellar medium. Solar particles still cross the region in small numbers, and some interstellar particles enter the heliosphere, so the heliopause is not an impermeable wall. It marks a change in which plasma and magnetic field dominate the local environment. Voyager 1 reaches this boundary at about 122 astronomical units from the Sun. Voyager 2 crosses it at about 119 astronomical units. Their instruments record changes in charged particle populations and magnetic conditions that identify entry into interstellar space. Though both spacecraft remain gravitationally bound to the Sun, neutral atoms can pass through the heliopause more easily than charged particles because magnetic fields do not guide them in the same way. Some interstellar hydrogen enters the heliosphere and is later ionized by sunlight or collisions. Once charged, these particles are carried by magnetic fields and can become pickup ions, meaning ions gathered into the solar wind after entering from outside. Their behavior helps astronomers study the interaction between the Sun and nearby interstellar gas. Energetic neutral atoms also provide a way to map the boundary from near Earth. Missions such as NASA's Interstellar Boundary Explorer detect these atoms after they travel inward from the outer heliosphere, revealing broad structures that ordinary telescopes cannot see. One of these structures is a narrow band of enhanced energetic neutral atoms known as the ribbon. It curves across the sky and appears connected to the direction of the local interstellar magnetic field. Its exact formation involves interactions among particles and fields near the heliopause. Several models reproduce parts of the observed pattern, though details remain under study. The ribbon demonstrates that the Sun's boundary responds not only to outward pressure from the solar wind, but also to the magnetic environment of the surrounding galaxy. The heliosphere is shaped through contact between two moving plasmas, each carrying its own field and particle population. Schultz's star passes far outside this particle bubble. Its estimated closest distance is about 50,000 astronomical units, while the heliopause lies only a little beyond 100 astronomical units in the directions crossed by Voyager. The gap between the binary and the heliosphere is therefore hundreds of times larger than the heliosphere itself. At that range, the star's own wind and magnetic field cannot push directly against the Sun's boundary in any significant way. The interstellar material between the two systems remains the immediate environment of the heliosphere. Any radiation from the faint red dwarf and brown dwarf companion also arrives too weakly to alter the solar wind or reorganize the heliopause. The passage leaves no known particle signature preserved within the heliosphere. Solar wind material flows outward and is replaced continuously, while magnetic structures change with the Sun's activity cycle. a brief disturbance would not remain fixed for tens of thousands of years. Schultz's star also produces no known rise in cosmic rays large enough to leave a distinct record. Its low luminosity, small mass, great distance, and rapid passage keep its influence beyond detection in this region. The heliosphere continues to breathe around the Sun, expanding and contracting slightly as the solar wind changes, while the faint binary remains far outside its moving boundary. Inside the Kuiper belt and the outer reaches of the heliosphere lies the region governed by the 4 giant planets. Neptune, Uranus, Saturn, and Jupiter move around the Sun on broad, nearly circular paths, each carrying a system of moons, rings, dust, and magnetic fields. Their masses make them the dominant bodies beyond the terrestrial planets, yet even together they contain only a small fraction of the Sun's mass. The Sun therefore remains the central source of gravity throughout this region. Each planet follows an orbit determined mainly by the Sun, while the planets also pull on one another and exchange small amounts of orbital energy over long periods. These mutual effects create a complex but stable pattern that has persisted for billions of years. Neptune travels farthest from the Sun at an average distance of about 30 astronomical units. It completes one orbit in roughly 165 years. Its deep atmosphere contains hydrogen, helium, and methane, with winds moving through high clouds and darker layers below. Triton, its largest moon, follows a backward orbit compared with Neptune's rotation, indicating that it is probably a captured world. Neptune's gravity controls many nearby small bodies and shapes resonant populations farther outward. Within the giant planet region, however, its own orbit remains strongly bound to the Sun. A distant passing star at tens of thousands of astronomical units creates no meaningful displacement in Neptune's path. Uranus moves at an average distance of about 19 astronomical units and completes an orbit in about 84 years. Its rotation axis lies almost within the plane of its orbit, giving the planet an extreme tilt. This orientation produces long seasons as each pole turns toward or away from the Sun during different parts of the Uranian year. The planet contains hydrogen and helium in its outer layers, along with methane that absorbs red light and gives the visible atmosphere a blue-green appearance. Beneath the atmosphere lies a deep interior rich in water, ammonia, methane, rock, and other materials compressed under high pressure. Uranus has faint rings and a family of moons whose orbits remain tied securely to the planet. Saturn travels at an average distance of about 9.5 astronomical units and circles the Sun in nearly 30 years. It is less dense on average than water and consists mainly of hydrogen and helium. Its most visible feature is the broad ring system made largely of the water ice particles, ranging from tiny grains to much larger fragments. The rings occupy a wide disk, but are thin compared with their diameter. Saturn's gravity organizes these particles into gaps, waves, and narrow bands, while moons embedded within and beyond the rings add further structure. Titan, the largest Saturnian moon, possesses a dense nitrogen atmosphere, methane clouds, and lakes of liquid hydrocarbons. Enceladus releases water-rich plumes from fractures near its south pole, revealing an ocean beneath its icy surface. These local systems respond to gravity on scales far smaller and stronger than any force from Schultz's star. Jupiter is the largest planet and the most massive object orbiting the Sun. Its average distance is about 5.2 astronomical units, and its year lasts a little less than 12 Earth years. The planet contains more mass than all the other planets combined. Hydrogen and helium dominate its deep atmosphere and interior, while clouds of ammonia, water, and other compounds form visible belt zones and storms. The Great Red Spot is a long-lived rotating storm larger than Earth, though its measured size changes over time. Beneath the clouds, pressure increases until hydrogen behaves as an electrically conducting fluid. This layer helps generate Jupiter's powerful magnetic field, which surrounds the planet with a vast magnetosphere filled with charged particles. The 4 large moons discovered around Jupiter in the early 17th century remain among the most important worlds in this region. Io experiences intense tidal heating as Jupiter and neighbouring moons continually flex its interior, driving widespread volcanism. Europa has an icy crust above a global ocean of liquid water. Ganymede is the largest moon in the solar system and generates its own internal magnetic field. Callisto has an ancient, heavily cratered surface and may also contain a deep ocean. The motion of these moons is controlled by Jupiter the Sun and their mutual gravitational relationships. Their resonances repeat in regular patterns and produce tidal forces far greater than the faint differential pull of a remote passing binary. Across the giant planet region, orbital stability does not mean that nothing changes. The planets perturb one another continuously. Their orbital shapes and orientations vary slightly over long cycles. Small bodies can be captured, temporarily redirected or ejected after close encounters. Comets entering from distant reservoirs may pass among the giants, and Jupiter often produces the strongest change because of its mass. A comet can lose energy and enter a shorter orbit, gain energy, and leave the solar system or collide with a planet or moon. These changes arise from close local encounters in which distances may be only thousands or millions of kilometers, not trillions of kilometers. Schultz's star passes at a distance of roughly 50,000 astronomical units. Across the much smaller scale occupied by the giant planets, its gravity pulls almost equally on the Sun and on every planet. A nearly equal pull changes the motion of the entire system together, but produces almost no change in the planet's positions relative to the Sun. Only the tiny difference in attraction across the planetary region can disturb an orbit. That tidal difference is exceedingly weak. The binary's combined mass is far below the Sun's mass, and its high speed limits the time available for gravity to act. Calculations of the encounter show no measurable alteration to the paths of Neptune, Uranus, Saturn, or Jupiter. The giant planets also protect no fixed boundary around the Sun. Their gravity can redirect small bodies, but it does not shield the system from every distant influence. In this case, protection is unnecessary because the passing star remains too far away to threaten planetary stability. The known moons stay bound, the rings remain organized, and the planetary orbits continue without a detectable change. The encounter belongs to a scale so much larger than this region that it becomes only a nearly uniform background pull. Around the 4 giant worlds, gravity is governed by the Sun, the planets, and the close companions moving beside them, while Schultz's star passes through remote darkness with no known physical effect on their enduring motion. Inside Jupiter's orbit, the solar system becomes warmer, brighter, and more tightly bound to the Sun. The asteroid belt occupies the region between Mars and Jupiter, while Mercury, Venus, Earth, and Mars move through the inner planetary system on shorter and faster orbits. These worlds and smaller bodies are separated by millions of kilometers, yet the entire region is compact compared with the distance of Schultz's star at closest approach. Solar gravity dominates every orbit here. The passing binary remains so remote that its attraction acts almost equally on the Sun, the planets, and the asteroids, leaving their relative motion effectively unchanged. The asteroid belt extends mainly from a little beyond 2 astronomical units to somewhat more than 3 astronomical units from the Sun. It is not a crowded field. Most asteroids are separated by large distances, and spacecraft pass through the belt without weaving between closely packed rocks. The total mass of all known belt material is less than the mass of Earth's moon. Much of that mass is concentrated in a few large bodies, including Ceres, Vesta, Pallas, and Hygeia. Ceres is large enough for its gravity to shape it into a rounded world, and is classified as a dwarf planet. Its surface contains hydrated mineral salts and water-rich material, while evidence indicates that brines may still exist beneath parts of its crust. Vesta is smaller but preserves a layered interior. It has a crust mantle and metallic core, showing that early heating allows it to separate into distinct materials. A vast impact basin near its south pole sends fragments into space, some of which later reach Earth as meteorites. Other asteroids remain irregular because their gravity is too weak to pull them into spheres. Their compositions range from dark carbon-rich material to brighter silicate rock and metal. These differences reflect temperature-location collisions and mixing during planetary formation. Jupiter's gravity strongly shapes the belt. Certain orbital distances contain gaps where repeated gravitational pulls make long-term motion unstable. These are called Kirkwood gaps. Other regions contain stable groups whose orbital periods maintain regular relationships with Jupiter. Collisions also alter the population. Some impacts break parent bodies into families of fragments that share similar paths and compositions. Smaller fragments drift slowly because sunlight produces subtle thermal forces. Over long intervals, some enter resonances that deliver them toward Mars, Earth, or the Sun. These processes create changes far larger than any caused by the ancient stellar passage. Mars travels just inside the main belt at an average distance of about 1.5 astronomical units from the Sun. Its thin atmosphere consists mainly of carbon dioxide. Iron-bearing minerals in its soil give the surface a reddish color, while volcanoes, canyons, ancient river valleys, and sedimentary rocks record a complex history. Evidence shows that liquid water once flows across parts of the surface and collects in lakes. Today, most accessible water exists as ice in the polar caps beneath the ground and within minerals. Mars completes an orbit in a little less than 2 Earth years, held securely by solar gravity and influenced only slightly by the other planets. Earth moves at 1 astronomical unit from the Sun. Its orbit is nearly circular, and its moon travels around it while the pair follows the Sun together. Oceans cover most of the surface, and the atmosphere contains mainly nitrogen and oxygen. Earth's gravity-magnetic field atmosphere and internal heat create an active planet. Tides arise mainly from the Moon and the Sun. The planets produce smaller orbital effects over long cycles, but a star passing 50,000 astronomical units away adds no measurable force to these influences. Its light remains faint, and its gravitational pull is nearly uniform across the Earth-Sun system. Venus travels closer to the Sun at roughly 7/10 of an astronomical unit. It is similar to Earth in size, but has a dense carbon dioxide atmosphere and clouds containing sulfuric acid. A strong greenhouse effect keeps the surface at temperatures high enough to melt lead. The planet rotates slowly and in the opposite direction from most planets. Its surface shows broad volcanic plains, mountains impact craters, and evidence of extensive geological change. Radar observations reveal these features through the opaque clouds. Venus completes 1 orbit in a little more than 200 Earth days, moving through a gravitational environment governed almost entirely by the Sun. Mercury occupies the innermost planetary orbit, averaging less than 4/10 of an astronomical unit from the Sun. It travels around the Sun in only 88 Earth days. The planet has a large metallic core, a heavily cratered surface, cliffs formed as the interior cools and contracts, and permanently shadowed polar craters containing water ice. Temperatures vary greatly between sunlight and darkness because Mercury has almost no substantial atmosphere to spread heat. The Sun's gravity is especially strong at this distance, and curved space described by general relativity becomes important in explaining the slow rotation of Mercury's orbital orientation. Across the inner planetary system, orbital motion can be measured with extraordinary precision. Radar spacecraft tracking, telescopic observations, and laser ranging determine positions over time. These measurements reveal small gravitational effects from planets, moons, asteroids, solar radiation, and relativistic physics. If Schultz's star had produced a significant disturbance here, its influence would need to appear as a lasting change in orbital energy inclination or timing. Calculations show that no such change is expected. The binary is too distant, too low in mass, and too fast. Its differential pull across the inner system is far below the effects produced by known local bodies. The stable architecture of this region arises from billions of years of evolution. Early collisions build planets and remove much debris. Jupiter prevents the asteroid belt from forming one large world. Later impacts reshape surfaces, deliver materials, and occasionally alter rotation. The planets perturb one another in regular secular cycles, meaning slow changes that accumulate across long periods without close encounters. These cycles influence orbital shape and orientation, but they remain products of the Sun and planets themselves. Schultz's star contributes no detectable chapter to that local history. Within the asteroid belt and among the four rocky planets, the ancient flyby is physically silent. Rocks continue circling the Sun, planets maintain their established paths, and moons remain attached to their worlds. The binary's gravity reaches the region, but it arrives as an almost identical pull on everything within it. With no meaningful difference from one body to another, the inner solar system moves onward, as though the distant star were not there. On Earth, roughly 70,000 years ago, the night sky appears rich with familiar lights. The Moon changes shape through its monthly cycle. Venus, Mars, Jupiter and Saturn move slowly against the stars. The Milky Way forms a pale band across dark skies untouched by artificial light. Human communities live across parts of Africa, Asia, Europe, and Australia using stone tools, fire shelters, and complex social knowledge. Above them, Schultz's star passes through the remote outskirts of the solar system. Its distance is unusually small for a stellar encounter, yet its light remains too weak to become a lasting object, visible to unaided human eyes. The faintness begins with the nature of the system. Its primary is a small red dwarf producing only a tiny fraction of the Sun's light. Much of that energy emerges at infrared wavelengths which human vision cannot detect. The companion is a brown dwarf and is dimmer still. At closest approach, the pair remains about 0.8 of a light-year from the Sun. This is close compared with the present distances of neighbouring stars, but it is still several trillion kilometres away. Light spreads as it travels, and the small amount produced by the binary is diluted across that enormous distance. Astronomers describe apparent brightness with a magnitude scale. Lower numbers mean brighter objects, and the faintest stars normally visible to unaided eyes under excellent conditions lie near magnitude 6. Estimates indicate that Schultz's star remains several magnitudes below this limit during its closest passage. Its steady light is therefore far too dim to stand out in the prehistoric sky. Even in clear air, far from smoke or moonlight, the system does not resemble a new star. It occupies one point among darkness without delivering enough visible photons to stimulate human vision. The red dwarf is magnetically active and can produce flares. A flare releases stored magnetic energy and briefly heats part of the stellar atmosphere, increasing radiation across visible ultraviolet, radio, and X-ray wavelengths. Some red dwarfs brighten greatly during strong events. Schultz's star may also produce flares during the period of its approach, since observations show that it is capable of magnetic activity. It remains uncertain whether any flare at closest passage becomes bright enough to be seen from Earth. No physical record establishes that such an event occurs, and no human record survives from the period. The scientifically secure conclusion concerns the faintness of its normal light, not an unobserved exceptional outburst. Even a visible flash would carry no obvious meaning for people on Earth. It would appear only as a temporary point in the sky with no detectable movement during a human lifetime. The binary's passage unfolds across thousands of years. Its motion relative to background stars is real, but the change from night to night is extremely small. Without telescopes, clocks, written catalogues, and precise instruments, no observer can identify it as a nearby system crossing the solar system's outer boundary. Its gravity produces no felt force, no alteration of seasons, and no change in the paths of the visible planets. Earth itself continues along its orbit without measurable disturbance. The sun rises and sets according to the planet's rotation. The moon drives familiar tides. Climate follows terrestrial, solar, and orbital influences unrelated to the passing binary. Around the time of the encounter, Earth experiences part of the last glacial period, with large ice sheets covering northern lands and climates varying across long cycles. Schultz's star provides no accepted explanation for these environmental conditions. Its distance and low mass leave the inner solar system unchanged, and there is no evidence connecting the passage with biological, geological, or cultural events. No crater sediment layer, isotope anomaly, or magnetic signal records the flyby. A star passing through the outer Oort cloud does not shed material across Earth in a dense wave. Interstellar particles are already present in the space around the Sun, and the binary remains too distant for its atmosphere or wind to reach the planets directly. Any comets weakly disturbed in the outer cloud require long spans to move inward. The encounter therefore leaves no immediate surface trace that later societies can discover. The passage becomes known through astronomy conducted many thousands of years afterward. Infrared sky surveys identify faint, cool objects that visible light surveys can miss. Schultz's star attracts attention because its proper motion appears small despite its relative proximity. A nearby star often moves noticeably across the sky, so the modest sideways drift seems unusual. Spectroscopic observations then reveal a large radial velocity directed away from the Sun. Spectroscopy separates light into wavelengths and shifts in absorption. Features show motion along the line of sight. The system is not moving slowly. Most of its speed is directed almost straight away from the solar system. Distance measurements complete the basic picture. Parallax records the tiny apparent shift of the star as Earth observes it from opposite sides of the Sun. Combined with proper motion and radial velocity, this supplies the three-dimensional position and velocity needed to reconstruct the path. Astronomers also resolve the brown dwarf companion and account for the binary orbit, refining the motion of the pair's shared center of mass. Computer calculations then carry both Schultz's star and the Sun backward through a model of the Milky Way's gravitational field. The result is not a photograph of the past. It is a range of trajectories consistent with measured data. Repeated calculations vary the input values within their uncertainties and show where the system most probably travels. These solutions converge on a close passage through the outer solar system around 70,000 years ago. Improved observations adjust the estimated distance and timing, but the central finding remains. A faint binary once becomes one of the Sun's nearest known stellar neighbors and departs without entering the planetary region. Humanity learns of the event only because modern astrometry turns minute shifts of light into a history of motion. The star leaves no story in oral tradition that can be identified, no visible monument in the sky, and no direct mark on Earth. Its passage survives instead in its present velocity. Every measured movement contains part of an earlier path. From that motion, the lost encounter emerges quietly, revealing that the solar system has never been isolated from the slow traffic of the galaxy. The solar system continues through the Milky Way, carrying its planets, moons, dust, and distant ice through a galaxy filled with other moving stars. Schultz's star is already far away, its faint binary light receding into the wider stellar field. Nothing remains near Earth to mark the passage. The planets continue along their familiar paths, the giant worlds hold their moons, and the frozen bodies beyond Neptune move through their long cold years. Farther out, the Oort cloud remains unseen. Its scattered objects travel through darkness on orbits measured in hundreds of thousands or millions of years. Some paths may still contain small changes left by the ancient encounter, though most remain governed by the sun, the galactic tide, and the slow influence of many passing stars. No single body provides a complete record. The evidence survives as motion probability and the quiet geometry of gravity. On Earth, the event belongs to a time before written history. Human lives continue beneath a sky in which the passing system is too dim to notice. The star produces no lasting brightness, no disturbance of the planets, and no known change in the environment. Its nearness exists only on the immense scale of interstellar space. Modern instruments recover the passage from tiny shifts in position and wavelength. The star's present movement becomes a path into the past. In this way, astronomy reveals an encounter that leaves almost no visible trace. The discovery does not describe a catastrophe. It describes the ordinary movement of stars through the galaxy, where distances slowly narrow, reach a minimum, and widen again. The sun continues onward, surrounded by its distant cloud of ancient ice. Other stars also continues along their separate courses. Across long ages, the solar system remains part of this calm and ceaseless motion, held within the larger gravity of the Milky Way.